All right, welcome back, everybody. So now that you've had a chance to try one out on your own, we are going to try to use Coulomb's law, especially this force version that you can see here, to try to solve this problem here, where we've got 3-point charges, A, B, and C, that are all in a straight line. The way that we're going to do this is not too different from how we've done force problems in the past, which is kind of to draw a free body diagram and see what that will tell us about the net force on each of the charges. I'll go ahead and start with charge A over here on the left. And I'm going to try to find the force on A by B and the force on A by C. And then I'll be able to add those two forces together. So I'm going to start with the force on A by C, because I know that those two charges are both positive, which means that they're going to be repulsive. So they're going to get pushed apart. I can also see how big this force is going to be by looking at the electric field that charge C produces at charge A's location. That points away from charge C, and then I remultiply that by plus Q to get the force. So if I draw a quick free body diagram here, here's the charge. I will get a rightward or leftward pointing force. That's maybe about that big. And I'll label that as the electric force on A by C. Now, I also want to figure out the force on A by B, and there's a few differences. One, the charges are now opposite sign. And so I can figure out the direction either by thinking, these opposite forces, or these opposite charges, rather, are going to attract each other. So A is going to get pulled to the right. I can also, again, think about the electric field. The electric field from B, because it's negative, points inward, and then I multiply by Q to get the force. The other thing I care about is how big is the force on A by B compared to the force on A by C. And what you might see here is that B has less total charge, right? It's minus 1Q instead of plus 2Q, but it's closer. In fact, it's twice as close as charge C. And so even though that numerator is going to go down by a factor of 2, the denominator is going to go down by a factor of 4. So that's going to win out, and we're going to get a force on A by B, which is twice as large as the force on A by C. And I'll go ahead and label this force here as well, Fe on A by B. And we can see just from using normal force vector addition that the net force on A is going to point here to the right and be about kind of 1 unit of FEAC, right? If we were to call this kind of 1 unit of force, this one would be 2 units of force because it's twice as big. So we got 1 unit pointing that way. All right, so let's switch colors, and then we will attend to the force on object C. So I'll again draw a little object here. We're going to do a free body diagram. So I'll start by drawing the force on C by A, which again, I know that that's a repulsive force. So C is going to get pushed to the right. I also know that those two forces, the force on A by C and the force on C by A, those are Newton's third law pairs. So I can actually draw this force as being exactly the same size as the force that I have labeled over on the other side. So I'll go ahead and label this as Fe on C by A. Now, when I go to calculate the force on C by B, again, the direction is going to flip around because it's attractive now, so it's going to point to the left. But I have a couple of factors going on, right? The size of the minus Q is the same as the size of the plus Q on A. So no real difference in the strength of the charge, just in the direction that the force is going to be. However, charge B is still twice as close to charge C as A is, which means that the force is going to be 4 times larger. And so if I go to draw this force, it's going to be not twice as big, but 4 times as big. And I'll go ahead and label this one Fe on C by B. And so when I go to add the 2 blue forces up, I again get this 1 unit pointing to the left. But when I go to add the 2 red forces acting on C, I get about 3 units pointing to the left. That's going to give me a greater net force on C than on A, or a smaller net force on A than I would have on C.